It is for me a great honor to introduce this MCA Prize talk by Carlo Pagano from Concordia University in Montreal. Carlo did his PhD in Leiden under the supervision of Lenstra, finishing in 2018. And we heard about his work at the prize ceremony. It was mentioned his work on the negative Pell equation and the proof of Stephen-Hagen conjecture. And today he will talk about his work on using elliptic curves to transfer undecidability results between different rings, which is used to settle Hilbert's 10th problem for more general rings. So,
thank you very much. It's a great honor to speak here. And yes, I'm going to talk about joint work with Peter Koymans, all coming from more or less last academic year. And we introduced in this work a new method that allows you to construct elliptic curves over general number fields that have simultaneously achieved two things. They have a positive rank, and this rank is in some sense constrained, is upper bounded, but I keep it vague for now because I will give two meanings of the word constraint throughout the talk. And if you don't know what elliptic curves are, what rank are, and I will clarify this. But for now, I want to tell you two motivations for this. One comes from mathematical logic, and it's somewhat broader, and it's, as Gonzalo was mentioning, is Hilbert 10th problem. And the other motivation is more number theoretic, and is get a better understanding of a rank of elliptic curves over number fields. And depending on what your motivation is, you might be more or less demanding on the results. We will see that when you have the first motivation in mind, you can prove essentially less precise results, while once you have the second one, you aim for optimal results. So, okay, so let me tell you more about the Hilbert 10 problem. So we heard other talks about other problems of Hilbert coming from this list of 23 problems that he posed at the second ICM in Paris in beginning of last century. And this was something that Minkowski pressed him to do, to pose sort of a list of problems that would have been thoroughly influential for mathematics, and that was the case throughout last century. So the 10th problem asks the following, and in the way Hilbert formulated back then, actually, it was not even a question. Hilbert had a very optimistic view of mathematics, and he really said, find a procedure that takes any polynomial equations with coefficients in z and is able to decide whether this equation has a solution in z or not. So, so he believed the answer to be yes. So this program for mathematics in particular, he was totally sure that the answer was positive to this. And it took 70 years to prove that the answer is actually no. And this was done progressively in two phases. There was first work started with Robinson, and then joined with Davis and Putnam. And in the 60s, they reduced the problem to a much simpler question. And Matiasevich, 10 years later, in his early 20s, was able to essentially finish the proof off. And they proved that no such Turing machine exists. So Hilbert dream sort of cannot be achieved when you aim for all polynomial equations with coefficients in z simultaneously. So let me tell you something about what essentially Matiasevich proved, which is the following curious statement that if you take the graph of the exponential function, so you send n in 2 to the n, apparently there is somewhere a polynomial equations which they construct explicitly, something like 54 variables, and it's a very complicated equation, but the property of this equation is that if you project the solution set in the first two variables, you get exactly the graph of the exponential function. So if you think equations that you can possibly solve over z, you will essentially almost never find such a behavior. So this is a very, very strange property. And you can say that essentially, it's a bit simplistic, but you can say that Robinson, Davis, and Putnam reduced the problem to finding such a graph, and Matiasevich was the one that 10 years later proved this result. So I will summarize this property of being the projection of a solution set with integer coefficients of the Z solution set by saying that a subset is Diophantine. And let me just say that the proof used cleverly, the Matiasevich proof for this statement used properties of the solution set of the Pell equation. And for as soon as you increase a little bit your number system, the proof broke down. So I can say more about this later, but let me just mention that once you prove that the answer is no over Z, this raises immediately the question for larger number system, like the Gaussian integers, or you can ask, what about the rational number? If the answer to Hilbert 10 problem was yes over Z, then it would have transferred immediately to many more number systems. But when the answer is no, then every larger number system becomes a new problem, essentially, unless you are able to reduce it. And then F did exactly that, was the one that had the insight that elliptic curves of positive and constrained rank might be a tool to transfer these undecidability results to larger number systems to smaller ones. And we will see more precise versions of what that means. And so in the 80s, this started this quest that sort of lasted quite some time, and people made a lot of partial progress on this, on finding criteria and using those criteria to find, to transfer these undecidability results. So this started the quest of elliptic curves. So let me say a few things about elliptic curves. So an elliptic curve is basically an equation of this form. Y squared is f of x, where f is just a cubic polynomial with coefficients in a field that has no repeated roots. And typically, you take the projective model of this, and there is a point at infinity. And the fact that it's cubic allows you to define naturally an abelian group structure by intersecting the curve with lines, essentially, that gives you 3 points that sum to 0. That's essentially defining this group structure. And if K is a number field, we know, and I will denote for the rest of the talk, E of K. E of K simply means you take the solution set where Y and X are in K. So that's all I mean by E of K. E of K is not just a group. If K is a number field here means a finite extension of the rational number. So finite dimensional vector space over the rational numbers and a field as well. So E of K is not just a group, it's a finitely generated group. So it has a well-defined notion of a rank, and this rank is, despite it's a simple invariant, is very mysterious. So we know very little about this function. For example, we don't even know that we don't even have an unconditional algorithm to compute the rank of an elliptic curve. I give you a cubic, and you, in finite time, decide the rank. We have sort of conditional way to do this under deep conjectures, but we don't know how to do this unconditionally. So it's an uncomputable function as far as we know at the moment. We don't know how to compute it. And there are even more embarrassing questions we don't know the answer to, like take the rational numbers. We don't know whether the rank is uniformly bounded. We don't know if it can be arbitrarily large. Noam Elkies sort of broke recently with Zev Klagsbrun his previous records, but it's somewhere close to 30, and it is conjecture to be bounded, but we just don't know. And the same is for any number field. And furthermore, there are very few integers that we know to be ranks of elliptic curves, like over any given number field. And I will make this more precise later, but previous to recent work, 0 was the only number that was known to be a rank of an elliptic curve over any number field. Like I give you a general number field, Mazur and Rubin were able to prove that, rank can be 0. All right, so I will mention an invariant that I will define very briefly for P equal 2. That is a certain vector space that upper bounds from above the rank when you take the dimension is called the P-Selmer group. And the only thing I want to mention for now is that this is a computable invariant. So we have computable upper bounds for the rank. There are quantities that we know how to compute that provably upper bounds a rank, but we cannot, that doesn't allow you to put your hands directly on the rank. All right, so this is a brief background on elliptic curves. So many people try to find precise instances of this vision of the NF, and the one that we are going to use is one proved independently by Björn Poonen and Sasha Schlappentock, and it's essentially the following, that if you have an extension of number fields and you have an elliptic curve over the smaller one where the rank stays the same and is positive, so this is an example of positive and constrained rank, then the ring of integers of OK is the projection, Diophantine, remember, means it's the projection of a polynomial equation with coefficients in OL. So there is a polynomial equation with coefficients in OL, such that if you project the first variable, is exactly OK. And you can think that that allows you to transfer undecidability results from OK to OL. Why? Because suppose you have a negative answer for OK, then you can simply add the equations that recognize that your variables are in OK to essentially say, OK, if I have an algorithm over OL, I can add these equations to write down an algorithm over OK, but that's a contradiction. So this is how this transfer works. If you prove that a smaller number system is a projection of a 0 set over a bigger number system, then you transfer undecidability results. So that's how the elliptic curves play a bridge between these undecidability results. OK, but you have to find elliptic curves. So that's the glitch. So people then immediately, for instance, if you find 1 over q, you are immediately done. If you can find 1 over q, you can prove that Hilbert result is as a negative answer over all rings of integers of number fields. And as I mentioned, we know embarrassingly little about ranks. So here is another basic problem that is tightly related to this and which circulated in this community of people working on this problem for a while. And it's, can you find over any number field an elliptic curve of rank 1? So even this very simple question was open until recently. And all of this was known, actually, if you assume one of the Millennium Prize problem, the Birch and Swinnerton-Dyer conjecture. And this is work of, very influential work of Mazur-Rubin in 2009. So both things were completely solved under BSD, under the Birch-Swinnerton. But that's still a very, very open problem. And so unconditionally, this was either of these things were unknown. So let me briefly recap. So we have this Hilbert 10 problem that asks for algorithms deciding solvability of polynomial equations in fairly general number systems like the integers or things closely related to the integers R. And the answer is that there is no such algorithm for R equals Z. This is this MRDP theorem from the 70s. The proof breaks down if you go to more general number systems. And however, the NF envisioned that you can use elliptic curve to transfer across number systems these undecidability results. And this comes down to essentially finding enough elliptic curves that have positive and unchanged rank in extensions. And this is due to Poonen and Schlappentock. And this was all known under Birch and Swinnerton-Dyer conjecture. So that was the status until 2024. And with Peter Koymans, we proved last December that if you take any finitely generated infinite commutative ring, so the one you like the most, you can take it, then Hilbert-Ten's problem over that ring is undecidable. So infinity is necessary because if your ring is finite, there is a simple algorithm to check whether an equation is solvable. You just test over all the elements of your ring. So that's not so interesting. So that settles sort of a Hilbert-Ten problem for all rings that look a bit like Z, that are at least finitely generated over Z, and they have infinitely many elements. And we deduce this by proving the Neff-Lipschitz conjecture that states that Z is a Diophantine subset of any ring of integers of any number field. OF here denotes the ring of integers of a number field. If you don't know what that is, it's some kind of higher dimensional version of Z sitting inside the finite extension of Q, which is F here. So this gets more and more specialized, and the actual result that we proved, and all the theorem 3 implies theorem 2, and theorem 2 implies theorem 1, this was already known, it's theorem 3. So our actual contribution is theorem 3. And let me finish here saying that, yes, it was already known that theorem 3 implies theorem 2 and theorem 2 implies theorem 1, though it's really not obvious. I mean, theorem 3 has this very bizarre assumption on 32 real places that essentially K is given by a polynomial equation, a irreducible polynomial equation with 32 real roots. So it's sort of a very special number field, but yet 2 is for general number field, and yet 1 is for general finitely generated ring. So there is work of other people going into the reduction steps. And our actual contribution is theorem 3. So this is what I want to talk about. Theorem 3 is this theorem that says that if you start with a number field having 32 embeddings in the real numbers, 32 different ring homomorphisms in the real numbers, then there is an elliptic curve that has positive rank over K, and if you add the square root of -1, the rank will not change. I is the square root of -1. So this is, there is this funny assumption on the 32 real places. It's enough for Hilbert-Ten problem, but if you care about elliptic curves and number theory, it's still not entirely satisfactory because there is this sort of random assumption on the 32 real places, and the extension is a very special extension. It's just square root of -1. So that's what I meant at the beginning. If your motivation is mathematical logic, you consider the business closed. But if you come from number theory, you want to understand the situation a little better. And that's, for instance, if you want to solve the question of curves of rank 1. And that's what we did in last May. And this was independently done by David Zivina using closely related methods, and we uploaded on the same day, basically. And the statement is that every number field contains an elliptic curve of rank exactly 1, and we deduce this from the following more precise theorem that for any sufficiently generic elliptic curve, and I will define generic in the next slide, having full rational two-torsion, you can find infinitely many quadratic twists of rank 1. I will define what quadratic twists are later in the talk, but it's a way to associate to an elliptic curve a family of elliptic curves defined over K, and they are parameterized by square-free numbers in K, basically. And this theorem is saying that as soon as the starting elliptic curve is sufficiently generic, you can find always infinitely many of such twists that have rank 1. So of course, this theorem implies the previous theorem once you say that there exists at least one generic elliptic curve. And let me just briefly say for number theorists in the room what generic means. If you are not a number theorist or this doesn't look familiar, you can just look at the final state bullet point. 100% of choices of curves of this form, y square is x minus a1, x minus a2, x minus a3, where a1, a2, a3 run in some box. For most choices, it's going to be generic. So generic here means something about the primes of split multiplicative reduction. There are enough primes of split multiplicative reduction. And they have to be of a sort of a special type, but that doesn't matter. For most choices of A1, A2, A3, you can find them. So, okay. So most curves are generic, basically, with full rational two-torsion. So having done all the motivation, for the rest of the talk, in the final 25 minutes, I will focus on these two theorems, Theorem A and Theorem B. They come in a very similar flavor. So I will focus mostly on Theorem A that states that you can find an elliptic curve over such a number field with 32 real places with unchanged rank and positive. And I will say something at the end on how you change the proof to adapt it, to remove the assumption of the 32 real places. So this bizarre assumption that you can see is not playing any role in Theorem B. It's removed with a slightly different technique, which I will explain at the end. So, OK, so before sort of losing the part of the audience that maybe is less familiar with these things, I would just want to give you an overview of the main ideas of the proof. So the proof is inspired by the probabilistic study of elliptic curves in natural family, which is tightly related with this Cohen-Lenstra distribution that Melanie was talking about in her first opening lecture at this event. So the family is what I mentioned is the quadratic twist family. So it's simply this family here that you start with f is fixed, and you start throwing in d. And d is a non-zero number, and you put it in front of y squared. And you might complain that this is essentially the same curve. You can absorb the d into the y taking square root of d. But that's something that is valid over the complex numbers or the algebraic closure of k, but is not valid over k. So you will change the solution set by doing that, and that is changing the rank. So the rank is now is a genuine moving function as you move d. And in such families, the computable upper bound for the rank coming from two descent, it's very well understood. It has a distribution, and people, starting from Heath-Brown and then culminating work of Smith, understand this pretty well. They can tell you the probability that this approximant rank is equal to 0, 1, 2, 3, 4, 5. So you have a good control on the upper bound. But that's not very helpful to, say, positivity, unless you assume big conjectures like Birch and Swinnerton dial. Remember, you want to constrain the rank, but you want to make it positive. So the constraint part is good if you have something like this results onto Selmer, but the positivity is still mysterious. So our approach, essentially, in a nutshell, our approach is to replace d with f of d. So if you replace d with f of d, then the condition on the positivity of the rank goes immediately out of the window. It's immediately enforced. The hard part goes back into the upper approximant. The upper approximants are very well understood in the family where d varies, in that case, dy squared. But when you vary d in f of d times y squared equal f of x, the control of this constraint on the rank becomes much, much harder. And there are no distributional results known at the moment, and it's considered a very hard problem. What we do instead is, instead of controlling the full probability, we take an input from additive combinatorics, from Green-Tao-Ziegler theorem for number fields, which was established here before, to find a suitable d that have small Selmer rank. So the main idea in a nutshell is this one, that you had these approximants that were understood in the family there. This goes out of the window when you make the rank positive. And then you balance this taking tools from additive combinatorics to get enough control on the upper approximants that make the rank both positive and constrained. So that's really like a very brief summary. Now we'll go into the actual details for the remaining 20 minutes. So our pool of curves are as follows. So let me fix some notation. There is a starting curve, which is y squared is f of x, and f has 3 roots in OK, in the ring of integers, a1, a2, a3. And as I mentioned, we look at this family where you twist by values of the polynomial f itself. And n is varying in k. So since n varies in k, so f of n is still in k, and you have this point x equal n and y is equal to 1. So this point, I will take care of this later. You can prove it's contributing to the positivity of the rank. It's a non-torsion point for most choices of n. So let me first massage this equation a little bit. And since n is in k, you can think of this as a rational number. So it's a ratio of two integers, m and d, m over d with d non-zero. So I can rewrite my equation as follows. So I can homogenize, I can multiply by d to the 4, and I can write it as a product of 4 linear forms. d, m minus a1d, m minus a2d, m minus a3d. These are 4 linear forms defined over k. So your twist comes as a bi-parameterized family of elliptic curves where there are two integer parameters, m and d, and that is the value of the twist. All right, so there are two demands for the rank for theorem A and two demands for the rank for theorem B. So I will explain in a second why the condition that the rank doesn't change in the imaginary quadratic extension is the same as saying that the rank of this other curve over k is equal to 0. So that I will explain in a second, but these two are very similar. So the one for B is a little silly. I'm saying that the number is equal to 1 by saying that it's positive and is at most 1. But in the proof, these play a very different role. The positivity is essentially coming from this point, and proving an upper bound for the rank is a Selmer computation where there is this additive combinatoric bit. So I'm not just writing a completely silly thing. I'm already telling you how the proof is organized by the two components. So, and the proof will go in a very similar way for the two things with a twist at the end. So let me just briefly explain this minus Fn here. So minus Fn is because we want to have that the rank doesn't change in the imaginary quadratic extension, but it's a true statement that the rank over the imaginary quadratic extension is always equal to the rank over k plus the rank of the quadratic twist by minus 1. And this is really not hard to prove. It's essentially the same proof that a complex number can be decomposed as a purely imaginary number, a purely real number, and essentially the proof in a nutshell is here. You take the ki points and you can norm it down with the generator of the Galois group of ki over k, and now you have that the left term is basically canonically the same as the k rational points on E minus, and the right term lives between 2 times the rational point and the rational point, so it's a group that has the same rank as the rational points. So the rank in the middle splits as the rank over k, which is the third term, and the rank of E minus still over k, which is the left term. So you have this decomposition of ranks, which justifies why here I want E minus to be 0, because it's a rank that is measuring the difference between the two ranks. All right, so this was, now that this is out of the way, let me recap the situation. We want the rank to be positive and the rank to be either 0 for the companion curve, the minus curve, or to be at most 1 for the curve itself, for the other theorem. Okay, let's get rid of the first red condition, the positivity of the rank. So we are considering this family of curves because they come with a point. But the fact that they come with a point doesn't mean that the rank is positive. It could still be that you constructed accidentally a torsion point on your curve. So you have to get rid of that condition. And this is the point, n, 1. So if you put x equal n and y is 1, you get a point on your curve. And here is the proof. The proof is basically that there is only a finite set of D for which there are more torsion points on ED than just the two torsion. And the two torsion is so explicit that you can make sure that that point was not two torsion. And we had a complicated proof, but in exchange with the journal, the referee found a much simpler proof of this, completely elementary. And essentially is the fact that we already have seen in a previous slide that you can embed the ED point into the K root D points that are where the Galois groups acts as minus. And once you do this embedding, you can deduce from this that the union of all the torsion points on the quadratic twist forms a set of bounded height, and it's also in a bounded degree. So by Northcott property, it's a finite set. All you have to check is that they don't intersect too much, and you can just check very easily that they intersect only in the two torsions. So so the two except from finitely many possibilities, you only see the two torsion, and it's very easy to check that this point you constructed is not two torsion. So that now becomes green, means that it's fine. We can go with that. So and you are still now struggling with the red condition, which is the hard part of the proof. So the hard part of the proof is to now enforce that the rank has an upper bound, either by 0 for the minus curve or by 1 for the actual curve, depending on which theorem. And this is a bit of a problem. I told you at the beginning of the talk that this rank is uncomputable. We don't know a way to compute the rank, so how am I going to do it? However, we have computable upper bounds for the rank. So now at least we can use those instead, because those are at least computable. Okay, let me replace it by imposing the condition on the upper bound instead. Because now at least I have computable conditions. So I've traded my uncomputable demands with the computable demand. It might be hard, but at least it's some problem where I put my hands on. I can put my hands on. So this is now at least a sufficient condition to conclude. Okay, how do you do that? So to tell you how we do that, I have to tell you a little bit about this two-Selmer rank. So this two-Selmer rank, yeah, I have to tell you how essentially you compute. It's not just computable. There is really an explicit algorithm to compute it. And, okay. So what is the two-Selmer rank? Let me just very briefly give you an ad hoc definition for this talk that gives you a flavor of which kind of animal it is. So there is a map injection of vector spaces coming from, if you take the k rational point of your elliptic curve modulo 2, it maps in the just pairs of square-free numbers, k star up to squares squared. And the map is simply the following. You take x and y, and you send it in x minus a, x minus b. And very unclear why this would be a group homomorphism here, but if you really want to go the brutal way, you can even check this by hand with the group law of the elliptic curve. So this map is not quite well defined when x is a or when x is b. Okay, for x equal a and x equal b, you can use that up to square the expression x minus a is equal to x minus b times x minus c. So you can move to something where x minus a is non-zero using the equation. So you can kind of cheat and define the same map also for a and b. When x is a and y would be 0, which would be not a non-zero number up to square. Okay, so what this approximation is the set of two-Selmer is the set of elements sitting on the target of this map, so of square-free numbers, basically, that at every prime come from the elliptic curve. So since we don't know anything about the rank, the first map would be no progress at all, because I don't know where are the rational points. But computing the local rational points is much easier. So if you just focus on the elements that are in the target that comes locally at every prime from such a map, then you are in better shape. And one can prove that is a finite dimensional vector space that gives you an upper bound for the rank, -2. Okay, so let me not say too much about it, just very briefly that you can describe this two-Selmer space quite explicitly. So the only primes where something interesting happens are the primes that are that are of bad reduction, or the two-adic places, or also the infinite places. So two-Selmer is basically a set of pairs of square-free numbers that are supported only at the places where the elliptic curve, the equation of the elliptic curve becomes singular. So when you twist, what that means is that it's pairs of square-free numbers that are basically supported in D, plus some little junk that comes from the starting elliptic curve. And for P that divides D, you have a completely explicit formula for what this local two-Selmer condition should be. So it's given by that, where these numbers, alpha, beta, gamma, are basically the differences of the roots. So if you're completely lost at this stage, the upshot of this is that this two-Selmer is basically computed as a certain matrix of Legendre symbols in the prime factors of D. So if you know the assignment of Legendre symbols between the prime factors of D, there is a matrix that you can write down. It's an ugly big matrix that computes this upper bound for you. It computes this space that upper bounds the rank. Okay, so let's make an overview of our situation. We have these two demands for A and B, and we want to control this two-Selmer. And I told you that essentially this two-Selmer is a matrix of Legendre symbols on the prime factors of these four linear forms. So you have now to control the matrix of Legendre symbols on the prime factors of four linear forms simultaneously. So it means that you need to have some control on the factorization of these four linear forms, and you need to know how the mutual Legendre symbols behave. Okay, that's already clearly a difficult problem because we know very little about prime factors of values of polynomials, in particular of prime factors of four linear forms simultaneously. So yeah, let me, here is a reminder what the connection between M and D is and N. So the red demands is basically that this matrix M has largest possible rank. It's almost invertible. And how do you do that? How do you do that when you at the same time need to know something about the prime factors of these four linear forms? And the main idea of this work is to basically invoke at this stage additive combinatorics to make these four guys primes or almost primes and have enough control on the matrix M that you can make it invertible. So that's in a nutshell what the idea is. So this is basically the first thought. We have this matrix of Legendre symbol. We want to make it invertible. OK, then just make them prime using Green-Tao-Ziegler for number fields. And this was proved by Kai in 2023. And you can think essentially probably you are done at this stage. Unfortunately, there is a problem that there is still this delta. And this delta might have 1 million prime factors. And the minor coming only from delta, omega is the minor of the matrix coming only from delta, is completely out of your control. It's fixed. It's there from the beginning. And you have to do something about it. Because if you make these guys primes, you are adding only a bounded number of rows to a matrix. If you start with a minor that is a zero minor, you want to make your matrix almost invertible, you add, I don't know, 4 rows. Yeah, the rank is just maybe gonna go up a little bit, but you are not gonna make it invertible. Instead, you can imagine if you start with a zero matrix and you make a very, very long process where you put 0 here, 1 here, 1 here, you are again with an invertible matrix, and then you have maybe 4 steps. So this is a problem, and you have to do something about it. So the second thought is that you are not going to make them prime. You are going to make them almost prime. So one, you use an auxiliary number that depends only on the original elliptic curve that does exactly this process of massaging the initial nullity of the matrix and essentially slimming down the initial value of two-Selmer to something manageable. And that's exactly what we do. So let's say that you put this number kappa in D. And Green-Tao-Ziegler, in the way proved by Kai, allows you to do that. You can make with a change of variable D kappa times a prime and the other 3 linear forms prime. OK, so let me continue. We have this second thought now that you make D kappa times a prime and the other 3 linear forms prime, and you want to still make your matrix basically invertible. And the role of kappa is to lower the original, to tame the original nullity of this sort of dark starting minor that is there from the beginning, and you cannot do anything about it. And that's all very nice, but there is a second problem, which is fairly serious. Additive combinatorics can make for you prime these 4 linear forms, but tells you nothing about their mutual Legendre symbols. You just don't know what that is. And actually, if you play a little bit with Euclidean division, you can essentially see that up to control symbols, that is the symbol M over D. So this symbol M over D, we asked also experts in this area, and they told us that there is no such results available at the moment, and this is a non-trivial problem to, at the same time, make everything prime and control this symbol M over D. Say that is as you please, basically, -1 and 1. OK, so the third idea then is to exploit matrix rigidity. So matrix rigidity is simply the idea that sometimes you might not know anything about a little corner of a matrix, but still know that the matrix is invertible after all. Here is a silly example. If you have a 1, 1, 1, 1 upper triangular with all zeros below, you don't need to know anything of what happens above the ones. That's a part of the matrix that is irrelevant. The matrix is going to be invertible anyways. So that's a silly example, but there are many more patterns that you can exploit in that. And so the idea is that maybe there is a way to enforce the rest of the matrix in such a way that it doesn't even matter what Qi and Qj is. The matrix is going to be invertible anyways. So building on work of Klagsburg, Mazur, and Rubin, this essentially comes down to make sure that the part before the green tau primes, the part supported only in the auxiliary kappa and delta and 2, has a dimension exactly 6. And furthermore, you need that the reduction of this space, the space coming from that minor, modulo the 3 new primes as full dimension. Essentially, you can prove that this is the, if you want to ignore the symbols from how this matrix is constructed, this is the only thing you can do. And this requires you only to know what kappa, how the Qi reduce modulo kappa, and that's completely fine. On the other hand, there is a problem that you know that the Q1, Q2, Q3 modulo any divisor of kappa, they are all the same number m. That's written in front of you. D is kappa times something. So when you reduce Q1, Q2, Q3 modulo D, for instance, so modulo kappa as well, you always get m. So Q1, Q2, Q3 are doing all the same thing modulo kappa. And on the other hand, you want divisors of kappa to go as independently as possible modulo Q1, Q2, Q3. So it almost feels you are in danger here. And the thing is that when you swap the demands, so in quadratic reciprocity, it's not exactly the same. So what Q1, Q2, Q3 do modulo kappa, modulo squares, is not, it's very related to what kappa does modulo Q1, Q2, Q3 by quadratic reciprocity, but it's not exactly equal. And in theorem A, our idea was essentially to use these extra real places to swap as independently as possible the Legendre symbol. So let me just give you a very quick example, and in the interest of time, maybe I'll go very briefly about it. So here is an example of two numbers that reduce in the same way modulo Q1 and Q2, but you know that their signs and the sign of Q1 and Q2 are sorted out in a way that you see, despite Z1 and Z2 are the same modulo Q1 and Q2, when you swap the symbol, you get upside down. So yeah, that's a very toy example. It's a bit more complicated what happens in the proof, but in theorem A, essentially, we use the 32 real places to disentangle this, to disentangle the swapping of quadratic symbols. Yeah, while here you see Qi, the Qi are constantly 1 modulo Zj. Okay, so the remaining minute, let me briefly mention that for theorem B, you have a fourth problem that there might be no real places at all. So this game goes completely out of the window. So the idea is to exploit places of split multiplicative reduction in delta and use the observation that the 3 linear forms are entangled modulo D, but they're still partially disentangled modulo divisors of delta. And you can find a matrix rigid assignment that sort of has a complete non-Archimedean analog of the Archimedean computations that we did in Theorem A. So essentially, the main insight for Theorem B is to replace the Archimedean places with places of split multiplicative reduction. So now both conditions are satisfied and you are happy. And yes, so in a nutshell, this is the summary that making curves with positive rank is not too bad. Upper bounding the rank is also not so bad, but doing both things at the same time was open until recently. And we found that additive combinatorics can be used as a bridge between these two words of positivity of the rank and constraint on the rank. And this method has been used in its sort of broad outline by two other groups. One is Alpozh, Bhargava, and Schnittman, and one is Zivina to prove this alternative, to give it alternative proof for Hilbert 10, and Zivina to give curves of rank exactly equal to 2. And I have some further directions here, but I will have to conclude now. Yes.
So you mentioned high conventionality, right? What about just hypercurves? Because it seems that...
I think it should be doable, but yeah, I know people are already working on this, and you could think to follow the same outline, but there is some non-trivial problem, I think, in constructing this auxiliary kappa there. And this matrix of Legendre symbol becomes significantly more complicated, but I think it sort of should be probably in the next 2-3 years. It will be done by somebody eventually. But I think it's doable, but there are non-trivial technical difficulties to overcome.
And just a question, what's special about I in your theorem? I mean, if you place I by
Right. Yeah, absolutely. I think with the technique of Theorem B, you can do any quadratic extension. As in theorem, if you follow the proof of Theorem B, we didn't write it down, but you can now remove in Theorem A both the assumption of the 32 real places and the assumption that it's the square root of -1. So using this trick of instead of the real places to swap the symbols, using the places of bed reduction, you can do any quadratic extension and over any number field. Yeah.
On the last slide, which is sort of related, the proof of Schlappenthal that you define Z over Q with just one universal quantifier?
Yeah, so the statement is that there exists, for a number field K, there is a polynomial P in, I don't know how many variables, but let's say many variables, at least 3, such that the first variable is in Q if and only if, for any value of the second variable, the rest of the polynomial has a solution in K. So this is all, it gets very close to say that Q is Diophantine over K, but there is this for all at the beginning of the sentence, which is not an existential definition. So that's the precise statement, that's what I mean.
K is any number?
Any number field, yeah, for any number field, and it uses the rank 1 elliptic curve.